Welcome to Tomorrow Unveiled.
We've been tracking the global energy transition for years now. We've watched this slow, steady march toward decarbonization.
Right. And for a long time, the story seemed pretty much set in stone.
Exactly. The narrative was fixed. Low density, intermittent sources, wind, solar, they would lead the way, and we'd back it all up with better and better batteries.
But the massive compilation of data we synthesized this week, it shows something fundamental has shifted.
It's not just a march forward anymore. This was a global, decisive pivot.
Okay, let's unpack that pivot, because it feels like it redefines both the physics and the financing of the future grid. We're calling this exploration green code, hot core.
And that title gets right to it. It introduces the central conflict and really the main takeaway from all the source material our dedicated research team pulled together.
So what is it? What's the pivot?
The whole energy transition is moving away from just, collecting low-density intermittent energy.
Sprawling wind farms, huge solar arrays.
Precisely. And it's moving toward actually generating firm, high-density power. We're talking about advanced thermal sources that are just always on, nuclear fission, advanced geothermal, and of course the big one on the horizon, fusion.
And the why behind this sudden pivot is all in those two terms. Let's start with the green code.
The green code is the demand side of the equation. It's the exponential, completely non-negotiable power demand from the artificial intelligence and data center revolution.
We're talking about a rise in computing loads that's just unprecedented. These systems need, was it 99.999% uptime? The grid cannot blink, not for a millisecond.
And if you can't blink, you need the hot core.
The hot core.
This is the supply side. It's the advanced thermal high-density energy sources that can deliver that kind of firm, reliable power. Whether it's fission from small modular reactors or the deep, constant heat from enhanced geothermal systems, and then there's fusion.
And this is where it gets really fascinating, because the financial markets, they moved with incredible speed this week.
Startling speed.
So, for everyone listening to Tomorrow Unveiled, our mission here is to explain why financial markets and government policy didn't just sort of nod at the hot core solutions this week. They backed them decisively with billions.
Our research team verified it. An extraordinary $6.75 billion in clean energy investments just flowed into nuclear and fusion technologies alone.
In a single 7-day period.
Yes, that's an order of magnitude increase in directed capital. It's a sea change.
That kind of capital shift isn't just a trend. It feels like a fundamental restructuring of global energy priorities. The market is screaming that it wants firmness and density over just cheap square footage.
And that distinction is all about physics. We have to lay this out, this dramatic physical difference between the energy sources.
Okay, let's do it. We're talking about energy density.
Right. The power output per square meter of land you use.
And for solar and utility scale wind, that number is pretty low.
It's roughly 2 to 20 watts per square meter of land. It's spread out. It takes up a massive amount of space.
Now compare that to the hot core sources.
Advanced fission, enhanced geothermal, future fusion plants. They're targeting an output somewhere in the range of 500 to 1,000 watts, sometimes even up to 1,200 watts per square meter.
So that density isn't just some engineering metric. It's the new currency. It's the currency of reliable decarbonization, especially when uptime is everything and land is finite.
The cost of intermittency has suddenly dramatically exceeded the cost of building dense, firm power.
And what this all means is that the AI boom, the green code, is the catalyst. A powerful, non-negotiable, and maybe entirely unexpected catalyst that's forcing the energy world to move faster and, well, think hotter.
Let's start right there. Let's detail the true scale of this AI demand.
Absolutely. The sheer scale of the green code. It's genuinely hard to wrap your head around because the consumption isn't linear. It's exponential.
Our dedicated research team has the numbers. Right now, data centers consume about 4 to 5% of global electricity.
And that's already a huge number. That's comparable to the entire energy consumption of a large developed country like Germany or Japan.
But the projections are, well, they're staggering. Because AI computation just keeps growing. These models, the large language models, they get exponentially larger, more complex.
And their power needs grow right along with them.
So by 2030, the current trajectory suggests data center electricity use could just skyrocket to 10, maybe 15% of the total global electricity supply.
We're talking about tripling or even quadrupling the power demand for a sector that basically defines modern life.
Yeah.
And it cannot afford a single flicker of instability.
And that extreme, nonstop need leads us directly to what we can only call the reliability crisis.
Right. When you're running these hyperscale computing clusters, millions of servers, trillions of operations a second,
Yeah.
intermittency just doesn't work.
It's physically incompatible. The fact that solar fades at sunset or the winds just, it breaks the model. Data centers need guaranteed power. 24/7, 365.
So this lack of firmness in the current renewable mix, that's the catalyst. That's what's driving this massive investment shift toward the hot core.
It's the single biggest driver.
Okay, there's a technical term we should introduce here because it really cuts through all the noise and gets to the economics of it.
Capacity factor.
Capacity factor. So in simple, practical terms,
Yeah.
what does that actually mean?
The capacity factor just tells you how often a power plant is actually running at its maximum potential. Usually measured over a year. It's really a measure of reliability.
Okay.
Low-density intermittent sources, your wind and solar, they typically operate at capacity factors between, say, 20% and 45%.
Because they're totally dependent on the weather.
They're fundamentally constrained by nature. So if you invest, I don't know, $1 billion to build a 1,000-megawatt solar farm,
You're not getting 1,000 megawatts all the time.
not even close. You can only realistically count on an average power delivery of between 200 and 450 megawatts. That's averaged out over the whole year, nights and cloudy days included. The rest of the time, that billion-dollar asset is just sitting there.
Okay, now compare that to the high-density sources.
Nuclear or geothermal. Because they're driven by a constant thermal source, either fission or deep earth heat, they operate at capacity factors of 90 to 93%.
That's a massive difference.
It's a gulf. A nuclear plant's output is nearly guaranteed. It's dispatchable. To get that same 93% reliability from an intermittent source, you need a massive overbuild too, maybe 3 times the nameplate capacity or just enormous long-duration storage systems.
Which adds huge costs and resource strain to that model.
Absolutely. Which brings us back to that analogy, which I think really helps make this clear.
Let's hear it.
If you're trying to power this modern AI metropolis, which is what data centers are creating, the low-density model solar and wind, it's like a big garden sprinkler system.
Okay, I see. It covers a huge area, that 2 to 20 watts per square meter, but it only works when the pressure is right.
Exactly. It shuts off when the sun goes down or the air is still, and you have to build these huge reservoirs, batteries, just to try and keep the pressure even.
So what's the hot core in this analogy?
The advanced nuclear or geothermal plant, running at 500 to 1,000 watts per square meter. That's the highly concentrated, always-on fire hose.
Tiny physical footprint, but massive constant pressure. No interruptions, 24 hours a day.
And when you have an AI model that needs that constant, high-volume, guaranteed stream of data, you need the fire hose. The difference in firmness, in density, in reliability. That's why the market is saying the low-density model alone just can't meet the green code's demand for power.
The market has voted for stability. And speaking of massive financial votes, the biggest headline this week has to be about the energy source that promises the ultimate high-density clean power, fusion.
It was arguably the most consequential step in the energy space this week. We saw a landmark merger, and it signals that fusion is moving. It's moving from a scientific curiosity in a lab to an actual publicly tradable investment.
That's the huge $6 billion transaction, the merger between Trump Media and Technology Group and TAE Technologies. This creates the first publicly traded pure-play fusion company.
And it's not just the valuation that's interesting. It fundamentally changes how capital markets can even access fusion. It offers a path for institutional investors into a world that was, until now, really just confined to venture capital.
It's a huge signal.
It is. It proves there's a viable path to public market capital for these companies, and that will attract a much, much broader pool of money. But we have to look at this critically.
Of course.
The huge valuation is attached to 2 very high-risk things.
Oh?
A highly speculative scientific endeavor and a company going public through a SPAC, a special purpose acquisition company, which has its own volatility.
It's a massive gamble.
It's a gamble. But the sheer size of the bet shows the confidence someone has in Takey's specific technology.
And that's what's so fascinating. Kiki isn't following the same path as, say, the huge international ITER project or a lot of its private competitors.
No, they're focused on what's called a proprietary field reversed configuration, or FRC, approach, and they're using a very specific fuel, hydrogen boron, or PB11.
And that fuel choice is everything. It's the key differentiator. It's why people call their technology the holy grail of clean density.
is. Most other fusion projects use deuterium-tritium, DT fuel, and DT is easier to ignite, it requires less heat and pressure, but 80% of the energy it produces comes out as high-energy neutrons.
And high-energy neutrons. They're bad news for the reactor itself, right? They don't care about magnetic fields. They just slam right into the walls.
They are absolute trouble. Neutrons penetrate everything. They degrade the reactor materials, make them brittle, which means costly repairs. And critically, they transmute the reactor vessel itself. They make it radioactive.
So you're creating radioactive waste.
It's shorter lived than fission waste, but yes, it's highly radioactive and there's a lot of it.
So if DDBC is easier but creates all these problems, what's the deal with PB11? Why is it so much harder?
The PB11 approach is what we call aneutron. It produces virtually no high-energy neutrons. Less than 1% of the energy comes out that way.
Aneutron.
The difficulty is that boron and hydrogen require exponentially higher plasma temperatures and pressures to fuse. It's a much, much harder engineering challenge. But the payoff is enormous. You essentially solve the reactor's materials problem from day one.
So the impacts are immediate, they're material, and they're financial. First, material longevity. The reactor vessel doesn't get brittle or radioactive.
So your capital asset lasts longer, and maintenance is far simpler and cheaper. Second, the energy output is mostly charged alpha particles, helium nuclei.
And because they're charged, they react to magnetic fields.
Exactly, which opens up the potential for direct energy conversion. Instead of using heat to boil water to drive a big, inefficient steam turbine.
Which is how every other thermal power plant works.
Right. You can theoretically convert that energy directly into electricity using electromagnetic fields, high-voltage rectifiers. It's a huge efficiency boost.
You bypass the entire mechanical process, you cut costs, complexity, massive physical parts, and you eliminate the thermodynamic losses from heat transfer.
Precisely. Traditional thermal plants are limited by the Carnot efficiency cycle. Direct conversion just sidesteps that. And there's a third benefit, fuel abundance.
Hydrogen and boron.
They're everywhere. They're non-radioactive, widely available. Boron is in cleaning products. This eliminates the huge, complex supply chain issues you have with breeding tritium for DT fuel.
It really does sound like a technology designed for infinite scale with minimal impact, if they can just crack the physics of ignition.
And this isn't just a theory anymore. The merger documents laid out a very aggressive commercial timeline. TAE plans to start construction on a 50-megawatt electric utility-scale demo plant in 2026.
That's not a lab experiment. That's real infrastructure.
With real financial stakes. They're targeting operational fusion by 2031 and then scaling up subsequent plants to 350, 500 mil away.
That puts them on a timeline that directly competes with the rollout of the most advanced SMRs, the small modular reactors.
It does. But we have to remember the global context. TAE isn't alone in this race. The data shows that overall private investment in fusion has now topped $10 billion.
A lot of people are betting on this field to solve the density problem.
And there's fierce competition. Our research team highlighted Commonwealth Fusion Systems, CFS. They've got huge venture backing. They just announced construction on their Spark tokamak, and they're targeting Q1.
Net energy gain, more energy out than you put in.
Right. And they think they can hit that in 2027. They're using a different technology, high-temperature superconducting, or HTS magnets.
What's the advantage there?
HTS magnets allow for much stronger magnetic fields in smaller devices. It dramatically shrinks the size of the reactor, which could make it more economical. The challenge, though, is the magnets themselves. They're complex to make, need sophisticated cooling, and their long-term reliability under constant neutron bombardment still needs to be proven, since they're using the easier DT fuel.
So we have these two distinct, highly capitalized tech raises happening at the same time. The FRC anetronic route and the HTS tokamak route, both racing toward commercial viability.
And the fact that both are hitting major construction milestones shows why the capital is finally flowing so freely into fusion.
But fusion, as spectacular as it is still years away. The green code needs firm power right now.
Today.
So the immediate solution is coming from a more familiar source. The second pillar of the hot core nuclear fission, and it's having a massive immediate renaissance.
Fission is the bridge. It's the proven, reliable, carbon-free, high-density source we can deploy today. And this week showed massive political and financial backing, especially in the U.S., positioning SMRs as the answer to the Green Code's reliability problem.
The U.S. federal acceleration is impossible to ignore. The Department of Energy, the DOE, announced $800 million in first-mover funding.
And that funding is so crucial. It helps projects cross that valley of death between getting regulatory approval and actually putting steel in the ground. That's the riskiest, most expensive part.
And the money went to two major teams, right?
Correct. The first is Holtec. They're deploying their SMR 300 reactor at the existing Palisades site in Michigan. And this is historic because it's a brownfield site.
A site that already had a nuclear plant?
Right. It already has the infrastructure, transmission lines, cooling permits, an experienced workforce that lets them bypass years of permitting headaches and community pushback.
And the other $400 million went to the Tennessee Valley Authority, TVA.
Yes, for GE Hitachi's BWRX 300 at Clinch River. And this reactor design is really important globally because of its radical simplicity.
How so?
The BWRX 300 is a boiling water reactor. Unlike most reactors, which are pressurized water reactors, this design eliminates massive, complex components like steam generators and pressurizers. It just boils the water right inside the reactor vessel.
And that simplification must have a huge impact on the supply chain.
It changes everything. Instead of needing these huge custom-made parts from a handful of global suppliers, many of the components can be standardized, mass-produced in a factory setting.
And what does that do for the cost?
Our research team notes this is projected to cut capital costs by up to 60% compared to a traditional large reactor. And on top of that, the design uses passive safety systems.
Meaning in an emergency, it doesn't need pumps or external power to cool down.
Exactly. It relies on natural things like gravity and convection for cooling and shutdown. That reduces complexity, manpower needs, regulatory risk. It's the key to making SMRs scalable. And it's the direct answer to the Green Code's demand for low-cost, high-speed deployment.
This political and financial push is also being matched by huge global policy reversals. It feels like that anti-nuclear psychological barrier is finally starting to weaken.
And the biggest example of that has to be Japan's Kashiwazaki-Kariwa restart.
This is a huge story.
It's genuinely enormous. The local government in Niigata Prefecture formally approved the restart of the Kashiwazaki-Kariwa nuclear power station. This is the world's largest nuclear facility. 7 reactors. And it's been mostly idle for 15 years, ever since Fukushima.
A definitive post-Fukushima reversal of policy in the one country that suffered the most profound psychological trauma from a nuclear incident.
If Japan, a country with limited space and extreme sensitivity to seismic risk, is accelerating restarts, that sends an undeniable global message about the need for high-density power.
And at the same time, China's moving ahead.
Yes, China's Linglong 1 SMR is on track to enter commercial service in the first half of 2026. That will be the first land-based SMR operation in the world.
Which sets a powerful precedent and forces Western companies to speed up just to stay competitive.
It does.
So we have new reactors, old ones restarting, money pouring in. But what about the historic problems with nuclear? Waste and efficiency, are those being addressed?
Dramatically. Through advanced fuel cycle breakthroughs, this is all about making nuclear fuel cleaner and smarter.
And we saw a big milestone there at the Idaho National Laboratory.
A major one. They achieved the first full-scale production of enriched uranium chloride fuel salt for the Molten Chloride Reactor Experiment, or MCRE.
Molten salt. Why is that specific chemistry uranium chloride fuel salt so important?
Because molten salt fuel lets you operate at much, much higher temperatures. We're talking 650 to 700 degrees Celsius compared to around 330 in traditional water reactors.
And for the listener, what does higher temperature mean in practical terms?
It means you get more energy out of the same amount of fuel. It's superior thermodynamic efficiency. And that high-grade heat is valuable for more than just electricity. You can use it to run high-temperature industrial processes, like making huge amounts of green hydrogen or providing heat for making cement or steel.
So it opens up entirely new markets for nuclear power.
New applications. Compact, high-efficiency power for ships or for remote industrial sites where you need a lot of power in a small package.
And then there's the other big innovation, turning waste into a resource.
This is incredible. Our research team notes the French firm Orano is now successfully extracting americium-241 from reprocessed spent nuclear fuel.
And using it for what?
To power long-lived radioisotope power systems. Americium-241 has a 432-year half-life, which makes it perfect for deep space probes or other things that need power for centuries without any maintenance.
So it closes the fuel loop. You take what was considered long-term waste and turn it into this ultra-dense, highly specialized fuel.
It completely reframes the waste problem. It's not a disposal burden anymore. It's a recoverable resource.
This whole section really shows fission isn't just recovering, it's evolving. It's becoming this flexible, efficient, cost-effective solution for that immediate need for dense power.
It is.
Okay, before we move on to the third pillar of the hot core, the deep heat right under our feet, let's just pause for a second and take stock.
Good idea.
We started with the exponential, non-negotiable demands of the Green Code and how that's exposed the reliability limits of low-density power. Then we saw capital just flooding into the high-density solutions of fusion and fission, both of which are scaling toward commercial reality by 2030.
These are major interconnected global trends, and we're only halfway through our analysis of this really pivotal week.
Right. We've covered the financial and tech breakthroughs, but the story isn't complete without looking at geothermal and the geopolitical strategy that's driving all these investments.
Exactly.
And if you're finding this insightful on YouTube, please take a moment to like this video, subscribe to Tomorrow Unveiled, and maybe consider hitting that new hype button to help us reach more viewers. And of course, turn on notifications so you never miss an update on the future.
And if you're listening on a podcast service like Apple Podcasts or Spotify, we would be incredibly grateful if you could leave us a rating and a review for Tomorrow Unveiled. It genuinely helps us reach new listeners and lets us keep compiling this essential information for you.
We love hearing your thoughts. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about this rapid policy shift toward high-density energy. Now, let's get into advanced geothermal, the quiet powerhouse of the hot core.
Geothermal is so often the forgotten resource in this conversation
It really is.
because it used to be so niche. But it offers the same critical advantages as nuclear. Carbon-free power with extremely high capacity factors, consistently operating up in the 90+% range.
The catch was always that you had to find hot water naturally close to the surface, right?
Yeah.
Which limited you to geological hotspots like Iceland or parts of California.
Like that's changing. It's changing dramatically with enhanced geothermal systems, or EGS. EGS is maturing. It's letting developers move past those geological constraints to access deep, hot rock virtually anywhere on Earth.
How does it work?
They drill deep, create an engineered fracture system in the rock, inject fluid, circulate it to pick up the heat, and then bring that superheated fluid back to the surface. It's essentially a closed-loop radiator using the Earth itself as the heat source.
And the ability to scale that up successfully depends on what?
Two things, really. Advanced drilling, and they're leveraging a lot of techniques perfected by the oil and gas industry there, and the hardware you need to process that massive volume of high-pressure, high-temperature fluid efficiently.
Which is where that big announcement from Exergy International comes in, the Gemini turbine. This seems like a piece of equipment designed specifically to solve the EGS bottleneck.
That's exactly what it is. This turbine is built for sheer power and volume. It's engineered for the high-flow, high-pressure demands you get from these deep EGS wells.
So it has a much higher power output.
Up to 60 megawatt electric per unit. That's often double the capacity of standard geothermal turbines. And crucially, it can handle over 50 cubic meters per second of fluid flow.
And why is handling that much fluid so critical?
Because to get a commercially viable amount of heat with EGS, you have to drill a lot of wells and circulate a massive amount of fluid. If you need to install 10 small turbines to handle that flow, your capital costs just go through the roof.
So being able to consolidate all that processing onto a single, efficient shaft, that's the game changer.
It is. The research team notes this one turbine is critical for cutting the capital expenditure, the CapEx of a project, by around 30%. This is how you make EGS economic everywhere, not just in natural hotspots.
And the financial world has definitely noticed. Fervo Energy closed a $462 million Series E funding round this week.
That is a massive investment for a technology many people considered niche just a few years ago. It shows serious market confidence in EGS.
And that money is going straight into hard infrastructure. The Keep Station project in Utah, they're targeting $400 million away of continuous, firm power by 2028.
And look at the investors. Google is a key participant. So is the heavy industry giant Mitsubishi.
So you have the convergence of tech and heavy industry, both chasing firm power.
Exactly. Google needs the firm power for its data centers. They need that 90+% capacity factor guarantee. And Mitsubishi is investing to secure a future for its turbine business in a post-carbon world. They're securing their spot in the hot core supply chain.
And there was another breakthrough that validates geothermal's role beyond just baseload power. It can also be used as storage.
Yes, the SAGE Geosystems project in Texas. This is fascinating.
What did they do?
They completed the world's first pressure-assisted geothermal energy storage system. It's 3 milliwares with 4 to 6 hours of duration. They use the geology itself as a battery.
Wow.
They inject high-pressure water into deep, sealed rock formations when power is cheap and abundant. That effectively pressurizes the subsurface, storing energy.
So when the grid needs power back, they just release the pressure, and that generates electricity without any battery chemistry.
That's it. They release the water, and the stored hydraulic energy, the pressure, drives a turbine on the surface. The heat from the rock helps with efficiency, but the power is coming from the stored mechanical energy. It's a huge breakthrough because it validates geothermal as a form of long-duration storage without relying on complex, chemically dependent batteries.
So geothermal isn't just a high-density generator. It can also function as a massive geological battery.
A triple threat technology.
That's right. So the total picture of the hot core is now complete. Fission, fusion, and firm advanced geothermal. All three seeing massive capital injections, all moving toward that 90+% reliability.
And now we have to look at how policy and major corporate money are reacting to this triple threat of reliable, dense energy.
We're analyzing the week where AI's green code demands fundamentally shifted global capital toward hot core solutions. And in the financial world, the most telling signal might be that massive $4.75 billion acquisition of Intersect Power by Alphabet, Google's parent company.
A landmark deal. And it illustrates a critical trend, vertical integration by tech giants. Historically, tech companies just bought power through power purchase agreements, PPAs.
Right, they'd promised to buy clean electrons for 15 or 20 years.
Now they are moving decisively to own their generation assets.
And the reason for that is about more than just emissions accounting. It's about bypassing the public grid, right? The congested transmission lines, the incredibly long interconnection queues.
That's a huge part of it. Our research team notes that the exponential growth of AI compute loads has simply outpaced the grid's ability to connect new generation sources, clean or dirty.
But it's also about control.
It's all about control. By acquiring Intersect Power, Alphabet gets control of a multi-gigawatt pipeline of assets. And most importantly, it lets them pursue a behind-the-meter grid model.
Meaning the power generation SMRs, geothermal, whatever, is co-located directly with the data center.
It insulates them from the instability, the delays, and the political risks of the public grid. For these tech giants, energy scarcity is now an existential business risk, and they're solving it by becoming power companies.
This financial strategy is being backed up by some very high-level geopolitical strategy. The U.S. National Defense Authorization Act, the NDAA, passed this week, and it included some critical legislation for nuclear power.
The International Nuclear Energy Act, INEA. The fact that this is included in the NDAA, the bill that funds the U.S. military, tells you everything. It funnels significant diplomatic and financial muscle to rapidly advance U.S. SMR exports.
Why are nuclear exports suddenly a matter of national defense?
Because it's a strategic geopolitical tool to counter Russian and Chinese influence. For years, Russia and China have used nuclear technology-building plants overseas, providing the fuel as a soft power tool. It links nations to their sphere of influence for decades.
So the INEA is designed to help UF SMR manufacturers compete for those first-of-a-kind deployments in places like Central and Eastern Europe, or Asia.
Offering a Western, secure supply chain alternative. The SMR is no longer just an economic asset for decarbonization. It is increasingly a fundamental tool for national strategic dominance.
And this strategic support for the hot core really stands in stark contrast to another major policy signal we saw this week.
Yeah.
It really illustrates this great policy bifurcation.
It does. While nuclear and geothermal are getting massive grants and export promotion, the low-density sector faced some serious political headwinds.
You're talking about the executive order that paused 5 major offshore wind projects on the U.S. East Coast.
Right. And the stated rationale, which we have to report impartially, was national security threats. Specifically, interference with U.S. Navy radar and other maritime defense operations.
And whether that rationale holds up or not, the impact is undeniable.
It injects massive uncertainty into the offshore wind sector. It halts billions in planned investment. And it signals that this administration is prioritizing hardened, secure, land-based power assets like nuclear and geothermal over these highly visible marine-based projects.
We should also touch on energy storage here, because it's the buffer for both the hot core and the low-density sources. And that sector is maturing incredibly quickly.
It is. We're seeing new chemistries that are denser and less reliant on geopolitically sensitive materials.
Our research team pulled 3 big announcements. First, solid-state batteries. Wellion achieved an energy density of 824 watt-hours per kilogram.
Which is huge. Current high-end lithium-ion cells are closer to 300 or 350 rh grams. That kind of density means you can store more power in a much smaller building footprint, which is vital for co-located facilities like data centers.
Second, sodium-ion batteries. Major players like CATL are targeting mass production by the end of 2025.
And sodium ion is critical because the materials are abundant. You can get sodium from seawater. It addresses the huge supply chain vulnerabilities you have with lithium, nickel, and cobalt.
And third, green hydrogen.
Everfuel demonstrated a 20 milliwatt hydrogen electrolysis plant that acted as a virtual battery. It absorbs surplus renewable power to make hydrogen, then can rapidly generate electricity back when the grid needs it.
So whether the solution is a nuclear plant or an advanced battery, that need for a dense, firm buffer is being solved in parallel.
It is.
Okay, let's move to our final section, where we compare the physics directly and explain why the land footprint, the physical sprawl, is so central to this entire debate.
The comparison of land use efficiency. This is a core argument driving the hot core transition. It hits on both environmental and economic factors at the same time.
Because you can't separate decarbonization goals from land conservation and habitat disruption. This is where physics and environmental stewardship really converge.
And it's all because of that massive density difference we talked about at the start, 2 to 20 watts per square meter versus 500 to 1,000.
And nuclear power requires 10 to 50 times less land per megawatt hour than wind or solar. Let's make that really concrete.
Okay, let's say you need 1,000 megawatt of constant power capacity, a major industrial load. A nuclear or advanced geothermal plant would require about 1,000 acres.
A concentrated, compact industrial footprint.
Now, for that same 1,000 megawatt capacity from utility-scale solar or wind, you'd need, conservatively, between 50,000 and 125,000 acres.
That's up to a 125-fold difference in physical sprawl. I mean, why should we care about that beyond just pure engineering?
Because land conservation isn't a peripheral concern in decarbonization, it's central. When you commit to a variable, low-density model, you are committing to industrializing massive tracts of land. You're potentially displacing agriculture, fragmenting critical wildlife habitats.
While high-density solutions, especially SMRs on existing brownfield industrial sites, they minimize that ecosystem disruption.
Exactly, and they reduce the cost and complexity of all the long transmission lines you need to connect remote, sprawling power plants.
Now, beyond land use, what about life cycle stewardship? Our dedicated research team compiled the life cycle assessments, the LCAs, which measure the total environmental impact of an energy source.
And the data there is really clear. Nuclear generation at 12 grams of co-euro equivalent per kilowatt hour is statistically comparable to wind power at 11 grams.
And critically, both are significantly cleaner than utility-scale solar.
Which comes in around 48 grams of co-euro hour, mostly due to the intense manufacturing and materials processing needed for the panels. So this data just decisively refutes that old narrative that nuclear is environmentally worse than renewables.
And the new reactor designs are also solving the waste problem. You mentioned fast reactors, like TerraPower's Natrium design.
They can convert up to 99% of uranium into fissile material. That shrinks the final volume of waste by a factor of 100.
It's the closed-loop waste cycle. Spent fuel, which used to be a problem for millennia, becomes fuel for the next generation of reactors.
Maximizing the energy you get from the original material and drastically reducing the volume and half-life of what's left.
And the third crucial physics point, one that's indispensable for the green code, is grid stability, or inertia.
This is vital for managing the spiky, high-volume demands of AI. Grid inertia is the system's resistance to sudden changes in frequency.
And traditional thermal plants, nuclear, geothermal, they have this naturally.
Right. They use massive spinning turbines connected to the generator. And these huge rotors store an incredible amount of kinetic energy, like a giant, stable flywheel.
And that kinetic energy is what stabilizes the grid against sudden shocks, like a huge data center load suddenly turning on.
It gives system operators critical time seconds, even minutes, to respond before the grid frequency collapses and you get blackouts.
And wind and solar just don't have that.
They lack that inherent stability because they use static inverters. They produce electricity without massive spinning mass, so they need expensive, complex battery control systems to electronically mimic the stability that the hot core provides naturally through physics.
So what does this all mean for the future grid? Is this a winner-take-all fight where the hot core just replaces low density?
Absolutely not. The research team's conclusions all point firmly to a hybrid reality,
A layered system.
a stratified system that uses the strengths of both. You need the hot core nuclear and geothermal, providing that 50 to 70% of reliable, firm baseload. That's the foundation that keeps the lights on and the AI models running.
And that foundation is then supported by the vast, cheap electrons from renewables. Solar and wind providing the other 20 to 30%.
Especially during peak output times to minimize fossil fuel use. And then finally, storage batteries, hydrogen geological solutions, they fill in the flexibility and short duration gaps.
It's about integration, not replacement.
The race is about integration, acknowledging the physical limits of each technology while maximizing their benefits.
We've covered a remarkable amount of ground this week on Tomorrow Unveiled. We've witnessed a truly historic shift in the global energy conversation.
To synthesize the big takeaways, policy, capital, and technology are all aligning now. They're aligning to solve the reliability problem posed by the green code, the exponential demands of AI, using the guaranteed firmness of hot core solutions.
The path to commercialization for small modular reactors, for fusion, for enhanced geothermal, it's never been clear. And 2026 is emerging as this critical demonstration year.
You have Chinese SMRs going commercial, US SMRs starting construction with huge DOE funding, a fusion company hitting the public markets, and large-scale geothermal projects securing $500 million investments.
And what this means for you, the person trying to understand where the future is going, is that the goal of deep, fast decarbonization, while also maintaining a highly reliable, modern grid, is now technologically feasible.
We have the physics, the technology, and the capital to do it. It is now fundamentally an execution challenge. Can we build it fast enough?
The days of purely theoretical energy debates, they feel like they're definitively over.
The deployment race is on, and it's being driven by the non-negotiable needs of the digital economy.
We truly appreciate you joining us for this exploration on Tomorrow Unveiled.
And finally, we'll leave you with one final thought, tying together the strategic, financial, and geopolitical threads of this week's news.
The proliferation of advanced nuclear technology, explicitly backed by national defense acts like the International Nuclear Energy Act, it raises a really important question for you to mull over.
In the emerging high-density energy future, is the power plant primarily an economic asset designed for rapid decarbonization? Or is it increasingly becoming a geopolitical tool for national strategic dominance in the 21st century?
Something to think about until our next look into Tomorrow Unveiled. Thank you for listening.